electricity. Now, resistivity is a function of temperature. There's an equation that you need to know, and here it is. PT is equal to PO times 1 plus alpha T minus TO. So this means that the resistivity of a metal is affected by the temperature. Now, the situation is different for semiconductors. For metals, as you increase the temperature of the metal, the resistivity decreases. It increases. I take that back. Not decreases. It increases. Now, why is that the case? Well, whenever you raise the temperature of the metal, the free moving electrons, they're colliding much more frequently. And so the drift velocity of the electrons caused by an electric current is much less because you have to go against all the random collisions that are occurring inside a metal. And as a result, metals, they have a much higher resistance at higher temperatures than at low temperatures. So metals conduct electricity better at low temperatures rather than at high temperatures. If you cool a metal enough, like to a very, very cold temperature, a metal can become a superconductor where there's virtually almost no resistance. So make sure you understand this. For metals, as you increase the temperature, the resistivity goes up. And so they have a higher resistance, which means that they're less conductive at high temperatures. Metals conduct electricity better at low temperatures. Now, semimetals or semiconductors, like carbon, graphite, silicon, germanium, the situation is different. As you increase the temperature, they become more conductive. They conduct electricity better, and their resistivity decreases. So it's different for semiconductors. Just keep that in mind. Metals, they have a positive temperature coefficient. So alpha is positive. That's the temperature coefficient of resistivity. And because alpha is positive for metals, if you can go to your physics textbook and look at the table for resistivity, you'll see that metals, they have a positive coefficient of temperature, which means that temperature and resistivity are directly related. If you increase the temperature, the resistivity go up. For semiconductors, they have a negative temperature coefficient, which indicates an inverse relationship. As you increase the temperature, the resistivity goes down, which means that semiconductors are more conductive at high temperatures, but metals are less conductive at high temperatures. So why is this information useful? Why do we need to know the relationship between temperature and resistivity? Well, sometimes you may want to digitally measure the temperature of an object, and you can use a digital thermometer for that. And it's based on this principle. By knowing the resistance of a metal at a given temperature, and if you can measure the resistance at a new temperature, you can calculate that temperature based on that new resistance value. Now, R is equal to P times L over A. So the ratio between, let's say, R2 over R1, that's going to be P L2 over L1. P2 times L over A divided by P1 times L over A. I didn't put a subscript for L or A, assuming that the wire remains the same. If it has a constant length and a constant area, and if only the temperature changes, then the resistivity will change only. So L and A will be the same, which means that they can be canceled in this equation. So if we keep the length of the wire and the cross-sectional area the same, the resistance will depend on the resistivity. And it makes sense. If you increase P, R will increase. So therefore, since this equation is PT over PO, or P2 over P1, we can replace it with R2 over R1. So we can say that RT is equal to RO times 1 plus alpha T minus TO. So if we have the resistance at one temperature, and if we can measure the resistance at a new temperature, then using this equation, we can calculate the new temperature or we can calculate the new resistance, whichever we want. And so that's how you can use resistance to measure the temperature of an object or even the temperature of a room using a digital thermometer. Now let's work